we have work out, which is W3, 4. And then for the heat addition process, this is our Q23. And lastly is the heat rejection process, whereby we have Q41. Okay. For a cyclic cycle, right? If we look here, if for a cyclic cycle, to get what is W net, we could get from the summation of work, which is equal to the summation of heat. So this is Otto cycle, which we are referring to the spark ignition type of engine. Yes, this is the air standard cycle. Air standard cycle. This is for Otto, which is used for the spark ignition engine. Right? Then we look at the analysis. We have looked for this. There's one parameter known as the compression ratio. The compression ratio is the ratio of V max divided by the V min. Okay, V max in this case is V1, the V min is V2. And this is equal to the swept volume plus the clearance volume divided by the clearance volume. So this is equal to Vs plus Vc divided by Vc, whereby the Vc in this case is equal to V2. Okay, the V2 is equal to the Vc. Right? And the Vmax is equal to Vs plus Vc. So the Vs is from this point to this point is Vs, from this point to this point is Vc. And to find out what is the efficiency of Otto cycle, this is W net divided by the Q in. This is our Q in, Q23. And if you look right here, the W net is Q in minus Q23 minus Q41, right? And if we assume that the CV is constant, in this case for air, then we have this type of equation, 1 minus T4 minus T1 divided by T3 minus T2. And looking at the compression and expansion process, which is the 1, 2, and also the 3, 4, we could write this equation, T2 over T1, as equal to V1 over V2, which is the compression ratio, gamma minus 1, which is equal to V1 equal to V4, and V2 is equal to V3, because it is isochoric. And this could be written also as T3 over T4 equal to R gamma minus 1. And then by substituting the T3 equal to T4, R gamma minus 1, and T2 equal to T1, R gamma minus 1. The final equation for the efficiency of in an Otto cycle is given as this, which is a function of compression ratio. And I explained yesterday what is the limitation of compression ratio. It all depends on type of fuel that being used. Okay? So this is a very simple example. Example 5.4. Let us have our own solution of this example. This text, this example or this text is taken from the McConkie textbook, okay? And I think, I don't know whether I put this textbook in my page or not. So let us do a very simple example to understand the concept or the usage of this compression ratio to get the thermal efficiency for this air standard cycle. Okay, so calculate the air standard cycle efficiency based on the Otto cycle for the petrol engine with a cylinder bore of 50 mm and a stroke of 75 mm and a clearance volume of 21.3 centimeter cube. So if you could sketch this cylinder, okay, we know that this is the Otto cycle, there's no valve involved. So this is our TDC. This is our BDC, bottom dead center. This is our bore. So let's say the bore is SD, 2 pi ND, 2 pi ND, LND. Okay, let's say this is as D, capital D. And let's say this is L, the stroke, the length of stroke. Okay, and then this volume we refer as the VC. And this volume we refer as VS. Okay, now given the bore, D is equal to 50 mm. Stroke L is given as 75 mm. And our clearance volume is given as 21.3 centimeter cube. Right? And we need to get what is the Otto cycle efficiency. For sure, we must use the equation that we have learned, right? Because we don't have any temperature given. It's only given the geometrical parameters, right? This is all the geometrical parameters of the cylinder. But we could get what is the thermal efficiency based on that. And for this equation of Otto efficiency, we are going to use the formula of 1 minus R K or gamma minus 1, right? In this case, the gamma is equal to K. And for air is 1.4, right? So we need to define what is R. R is the compression ratio, which is the Vmax divided by Vmin. In this case, what our Vmax? Vmax is the red color plus the area, the volume of the blue color, which is the Vs plus Vc, and the Vmin is the Vc. Then we got to get what is our Vs. The Vs is equal to, this is our Vs, the area of the bore or the piston multiplied by the length of stroke. Okay, and what is our A? A is pi d squared over 4 multiply the length of stroke is L. Okay, so can we calculate what is the Vs? Now we do Vs. In this case, we have the variance volume in centimeter cubic centimeter. Then we could use also the Vs plus Vc in term cubic centimeter. So let us look at the Vs. This is a pi. Our D in this case is the D is 50. Convert to centimeter. So minus 2. Correct? Is it minus 2? To convert 50 mm to centimeter. 10 centimeter. So it's not right. So 50 bagi dengan 10. Betul?
Bagi dengan 10, sir.
0.5. Betul? Betul
5, sir. 5.
Ya?
5. 5. 5 je.
Oh ya, 50, sorry. 5. 5. Squared over 4 multiplied by L. L is 75. So this is 7.5. So what is our Vs? Anyone? What is the Vs? Berapa guys?
147.3 cm.
1.3
147.3
cubic.
cm cube.
Okay. So calculate the Otto cycle efficiency. Okay, the R value first. So what is R value? R is equal to Vs is 147.3 plus the Vc is 2. Vc is 21.3 divided by 21.3. Okay, how much is that?
7.915.
7.915.
915.
Okay, for your information, the typical value of this compression ratio for a standard type of engine usually is in between 6 up to maximum you can go is up to 12. This is the typical value of R. Okay, usually for 12, usually is for high performance engine. Okay, for a normal engine is usually is 6 up to 12. 6 biasanya 6, 7, 8. Kalau motosikal digunakan 6. Untuk two stroke digunakan 6. Biasanya nilai dia. Okay, so when you put in your auto cycle efficiency, how much you got? 1 minus 1 over 7.915 power of k minus 1 is which is 0.4. And then multiply by 100 in percentage. How much is that?
$56.29. 56, sorry.
Yeah,
56.
556.
Yeah, 56.29.
56.29%. You see, this is the maximum efficiency based on Otto cycle. You can get only 56.29. Where does the rest of the energy go to? Why cannot get 100%? Yes, why we cannot get 100%? You only get 56.3. Where is the rest of the energy?
Exit as exhaust, sir.
Yes, this is the rejected type of energy. You see, we have rejected Q41. And also we have the input of energy, which is W12. So this Q41 and W12 is the rest of the energy. W12 is we need the W12. Okay, and the Q41 is the rejected heat. That's why we learn about thermodynamic. In the second law of thermodynamic, we have the definition of heat engine. Remember, we have the definition of heat engine. What is the definition of heat engine? We take the energy from TH, which is the supplied energy. Part of the energy is going to be converted to W net. The balance we are going to reject to the low temperature reservoir at TL, right? And then the whole heat engine is going to run as a thermodynamic cycle. So that is the definition of heat engine. If we don't have that parameters, the four characteristics of heat engine, the engine won't run. The engine will not give us a continuous work from the cycle. That's why we don't have 100%. And remember, this is based on the air standard cycle, which is the theoretical cycle. For actual cycle, we might have maximum can go is up 25%, up to 30%. Okay, we will look later. And towards the value of efficiency or depend on the driving condition or the operating condition of the engine. If you look a big engine when running at low load or low speed, low load, low speed, we might have up to maybe 5% thermal efficiency, up to 10% thermal efficiency. So it's all depend on the driving condition or what we said as referred as the operating condition of the engine. We cannot get only one value. Okay, the maximum can go is that 30%. But before that, when we drive the car, when we run the engine, we are going to have a certain value less than the maximum. So that we have to admit that is what we have from a heat engine. We cannot convert all the heat supply 100% getting all the W net in order to run the cycle. Okay? Any question, guys? Any question?
No, sir.
Ada Okay, kalau tak ada, we go for the problem that I took from that chapter of McConkie book 5.5. So this is question 5.5 from the McConkie textbook, okay, for the air standard cycle. In an air standard Otto cycle, the maximum and minimum temperature are 1400 and 15 degrees C. the heat supplied per kilogram of air is 800 kilojoule. Calculate the compression ratio and the cycle efficiency. Calculate also the ratio of maximum to minimum pressure in the cycle. Right? So we are talking about Otto cycle. So if we want to look the minimum and the maximum pressure, temperature, we could see it from the PV diagram. So what we are going to sketch right now is sketch the PV diagram of an Otto cycle. This is P, this is V. Otto cycle, constant volume for heat addition, constant volume for heat rejection. Okay, this is state 1, this is state 2, this is state 3, and this is state 4. We had a process of 1 to 2, we had a process of 2 to 3, and we had a process of 3 to 4. And we know that this is expansion and compression process is according to PV power of K is equal to constant, which is isentropic compression 1, 2 and isentropic expansion Q 3, 4. Okay? If we look at state 1, we have the equation of P1 V1 equal to mRT1. Sorry. If we look at state 2, we could have the IGES as P2 V2 equal to mRT2. And then for state 3, we have the IGES of P3 V3 equal to mRT3. And lastly, for state 4, we could have the IGES as a P4 V4 equal to mRT4. This is the equation, the ideal gas equation of state, which is based on state 1, 2, 3, and 4. Okay? And we have extra equation that also being called as IGES, but this IGES is being used for a given process. So 1, 2, 2. What do we have? We have P1 V1 over T1 equal to P2 V2 over T2. How do we get this equation, guys? The P1 V1 over T1 equal to P2 V2 over T2. Remember, we have learned this in our thermodynamic. How do we get that equation? Guys?
Same as flow rate.
Pardon?
Same as flow rate.
Same?
Mass flow rate.
This is a closed system. We don't have mass flow rate. Remember, this is Otto cycle. Otto cycle is a closed system. We don't have any intake valve. We don't have any delete or exhaust valve. So everything inside is air. Air is assuming as there's no valve, meaning that it's constant mass. It's a closed system. Okay, bukan mass flow rate, only mass. We get this from the equation of MR. This is MR at state 1, which is equal to the MR at state 2. Okay, at state 2. Because this is closed system, no combustion take place, then it's always air as our thermodynamic system. And we know that the 1 to 2, okay, 1 to 2 is a compression process. So can we substitute this, or can we simplify this equation? 1 to 2. No, we cannot simplify. That is the relationship that we have to use. Okay, we cannot simplify that. Right? But we do have extra equation whereby T2 over T1, which is equal to V over V K minus 1. Okay, which V divided by which V? Guys, which V divided by which V? V2 over V1 or V1 over V2? Yeah? Which one?
V1 over V2.
V1 over V2. Okay? And then next we have our relationship P2, sorry, P1 V1 gamma equal to, sorry, I put gamma, I use K just now, right? K equal to P2 V2 power of K. And another one, we have the T2 over T1 equal to P2 over P1 K minus 1 over K. So this is our TV relationship. This is our PV relationship. And this is our TP relationship. Okay, so this is the extra equation that we can use as far as the process of 1, 2 is concerned. Okay. Next, what do we have? The next one, we have the 2 to 3. 2 to 3. 2 to 3, we have PV over T equal to PV over T. This is 2, 2, 2. This is 3, 3, and 3. And we know that V2 is equal to V3. So this is what we have. The extra equation or the equation based on a given process from 2 to 3. Okay. And then we have another one is the 3 to 4. Again, we have the P3 V3 equal to P4 V4 over T4. That's it. We cannot do anything else. We cannot simplify. This is based on what? Based on the based on the reversible adiabatic or isentropic process, which is PV over K equal to constant. But we could write extra equation. For this 3 to 4 process, we have extra equation, of course, same as the what we have from the 1 to 2. The extra equation that we could write here is the T over T equal to V over V power of K minus 1. So if this is the after the expansion process, and this is 4, this is 3. Then this should be 3, this should be 4. Okay. Next one, we have the PV power of K is equal to PV power of K. This is 3, 3, 4, 4. Okay. And then next one, we have the T over T equal to P over P. This is K minus 1 over K. Right? So this is after the expansion process, which is 4. This is before. And then we have here is P4 over P3. So as far as the process 3 to 4, this is what we have. All the equation, the ideal gas equation of states involved. Right? And then for the last one is from process 4 to 1. 4 to 1, this is our 4 to 1. We have PV over T equal to PV over T. 4, 4, 4, 1, 1, 1. And we know that it is isochoric process or the constant volume process. So the volume can be cancelled off. So what we have right here is this equation. So now guys, you can see that as far as the state is concerned, this is the IGES for a given state. And then as for the process is concerned, 1 to 2, this is our equation, this is our equation, this is our equation, and this is our equation. Could be used. Okay, could be used to get all the parameters that we want, especially the PVT. Okay, the PVT. So 1, 2, and then we have the 2, 3, we have the 4, 1. Do we left anything, guys? We have 1, 2, yes. 2, 2, 3, yes. We have 2, 2, 3, 3 to 4. Kita skip 3 to 4. Dah sudah this is 3 to 4. So please remember all the equation that can be used. And this equation, that I have written right here is basically in order to solve for any value of P, V, and T. Okay, this is P, V, and T. Okay, now we look at the question. All right. Based on our cycle, the PV diagram, where do you think that this maximum temperature of 1400? Where is our maximum? 2, 3, 1, 2, 3, or 4? The maximum of this temperature, 1400 degrees C. What do you think? Where is the maximum temperature should be in our PV diagram?
3.
Yeah, why 3? Is it
Because higher pressure, more energy, and temperature.
because the state 3 is the state whereby we just supply the heat. Yeah, 2, 3 ni is the heat addition or the heat supply process. Of course, when we supply heat, the internal energy will increase, therefore the temperature will increase. So the given 1400 right here is given for the T3, the maximum temperature of the cycle. How about the minimum? (15 degrees C). Where do you think the 15 degrees C?
1.
Yeah, T1. Okay. T1 after the heat rejection process, which is 15 degrees C. Or you could look at your temperature profile. How we look at the temperature profile? This is our temperature profile of 3. This is the temperature profile of 4. This is the temperature profile of 1. This is the temperature profile of 2. So you can see that the minimum or the profile of temperature line will be least when it's going down. Compare 3 and 2, compare 4 and 1, we are going to have that the temperature profile of 1 is the lowest temperature profile. So meaning that the T1 is the minimum temperature. Okay? And then the heat supply. Where the heat supply? We know that the heat supply is at this point, at this process, which is 223. Therefore, we are going to look here, the Q23 for every kilogram of air. This is the heat input to the Q23, which is 800 kilojoule. Okay, so this is all the parameters given right here. What is the question? Calculate the compression ratio. So in order to calculate the compression ratio, then we need to get what is V1 and also the V2, whereby the V1 is the maximum volume and the V2 is the minimum volume. Okay, so right here, to get the compression ratio, which is R is equal to the Vmax divided by the Vmin. And in this case, the Vmax should be V1 and this should be V2. Meaning that we need to get what is our V1, right? So in this case, it's given right here the for every kilogram, for every kilogram. So what is our V1? This also could be written as in terms of specific volume. It's the same, V1 divided by V2. Okay. And if we look in terms of this unit, then we could also write the Q23 for every kilogram. Was given in the question based on for every kilogram for the heat supply, 800 kilojoule over kilogram. So how to get the V1? Of course, we use the IGES. The V1 is equal to PV equal to MRT 111. Then what is the V over M, which is equal to V. This is equal to, right? So we bring the M downward right here for every kilogram. So we are going to have the V equal to RT over P1. Okay, the T1 is given. This is T1. But this is, we need to get what is the pressure if we are going to use this formula. Okay, this formula to get the V. Right? So if we cannot solve for the V1 in this case, because we don't know what is the pressure. Okay, we don't know what is the pressure. Okay, so what are we going to do next? What do you think we could get next? Guys. So we have to convert everything in terms of pressure, right? So we have the temperature. So how to get, what is the term involved in this case? As far as the temperature is concerned? How about Q23? What do you think that we could get Q23? Q23 is equal to CV T3 minus T2, correct? We have the T3. CV for air. We have the Q23. So in this case, from this equation, we could solve for our T2. Okay? So get the T2 for me. Using the CV as 0.718. So this is this is 800 equal to 0.718. Okay, can we use the T3 as 1400 degrees C? Or do we need to convert it as in
Can,
Kelvin?
sir.
Can, because this is
sir.
delta. Okay, this is delta. So we can use 4000 minus T2. So get the T2. Get the T2.
To 5.8.
28
5.8 degrees Celsius.
T2 is equal to 2. Again, please.
285.8.
Okay, thank you. Degree C, right? Degree C. So now we have T1 and T2. Okay? So what we could use right here? You see? We have T1 and T2. T1 and T2. You see this equation? We want the compression ratio, right? The compression ratio is V1 over V2. So we could use this equation to get the compression ratio. Okay? So in this case, we know the T1 and T2. So what is T1 or T2? Sorry. T2 over T1 is equal to V1 over V2 K minus 1. Okay, now T2 and T1, can we use degree C? Here we use in degree C, right? Delta T. Right here, T2 over T1, in order to get the V1 over V2, okay, V1 over V2, which is equal to T1 over T2 over T1 power of 1 K minus 1. I ask again, can we use here in degree C?
No.
No, we cannot use degree C. We can only use in degree C if we are involving temperature difference. Right here, we must use this in Kelvin. This is also in Kelvin. Okay, so please get what is the value of V1 over V2. Apa guys? We should get around 5.27. Do you get 5.27?
Got 5.24.
Okay, maybe because of this value of CV. You got 4, eh? 5.24. Betul?
Yes, sir.
Okay, 24. Next, cycle efficiency. Then the cycle efficiency, when we have the compression ratio, then it's easy to get the compression efficiency. The cycle efficiency, which is the Otto cycle efficiency, which is 1 minus 1 over R K minus 1. So you can get the Otto cycle. And the next one is to get the maximum to minimum pressure. So what is our maximum pressure? P3. Okay, this is maximum pressure is P3. And the minimum pressure is P1. Okay, so you need to get what is P3 and P1. The maximum to minimum pressure. So the Pmax, Pmin, this is equal to P3 divided by P1. So how to get this ratio, P3 over P1? P3 over P1. Any idea how to get the P3? Can we get the P1? Guys, do you have any relationship here that we can get the P1?
The T21, P2 over
Yeah.
T1, sir.
P2
Over T1 equals to P2 over P1.
This one.
The down one, sir.
This one.
Yeah.
Yeah. Okay. From here, what do you get? From here, what do you get?
P1, sir.
P1.
P2 over P1.
P2 over P1. Okay. But right now we want what? We want P3 over P1. Yeah. So what we do, we look at the overall pressure ratio. Okay, overall pressure ratio. So if we look at the pressure ratio relationship, what is the overall pressure ratio? If we could write here, the P2, the P3 overall pressure ratio, the maximum over minimum is equal to P3 over P2 multiplied by P2 over P1. Okay? So you see the P2 cancel off, you get again P3 over P1. Then we could get the P2 over P1 by using this formula. Okay? P2 over P1, we could get from this formula. P2 over P1. And then as for the P3 over P2, P3 over P2, then if you look right here, is there any relationship that we could get? P3 is here the P3. So once we have the P1 over P2, and then we need to get the this equation is P2 over P1. 3, 1. Oh, we also could get the overall pressure ratio is P, yeah? Apa dia?
Kalau guna yang line 2-3 tu sir, P2 over P3,
P2 over P3.
yang T3 over T2. Boleh ke sir?
T3 over T2 tak boleh. Kenapa nak gunakan T2 over T3? Sebab kita dah dapat P2 dah. P2 P1 kita dapat. Now kita nak dapatkan dia P3 over P2. Okay? Ataupun kita boleh dapatkan P4 over P1. You see? So this equation also we could write as what? This is also is equal to, can we write that? P3 over P1. P3 over P1 is equal to P3 over P4 over P1 and P2 over P3. This no relationship. Kita bergas, kita stop dulu sini Kita sambung lah.
Sir, yang 2-3 ni sir.
Ya.
Saya tengok yang 2-3 tu, kan kita ada P2 over T2 equal
Yes.
to P3 over T3.
That's
Kalau
right.
kita transfer,
Boleh.
boleh?
So can. So kita gunakan ni This one. Because we already know the we have known the T2, we have known the T3, correct? So we could get the P3 over P4 from this equation. Okay? So guys, you have a try. Cuba buat. Dapatkan the same answer as this. This is compression ratio, this is thermal efficiency, and this is your pressure ratio. Pressure ratio. So we have kita ada dua pressure ratio and compression ratio. Compression ratio is V over V, pressure ratio is pressure over pressure. Okay? So please try buat soalan tu. Habiskan, siapkan, lengkapkan. Let me take your attendance. Ya, attendance. So this is your attendance. Okay guys, so next week the Tuesday semester, and then as you can see that I have given you the assignment which you have to submit next week on so next week perdana assignment 3. So this is our assignment 3. FT 242334. Right? So this is the question. Dalam PDF form. And this is the form that you can use, you have to use in order to submit your assignment. This is the question, and you could get PDF copy from this, download this assignment 3. Okay? Any question,
Yes,
guys?
That is
Any
it.
question? Okay,
For now, that is it.
yeah. Doctor, is due by what time? Time is 9 o'clock, 11:59. Midnight. Yeah, Iba? So on the 9, right. So saya akan switch off right on the dot lah. The last date of 9 May.